Hi there. I'd like to continue to talk about this paper actually, and I guess I made two videos. Just introduction of like graph cell processing and distributed graph filtering. So this is again this is a paper that trying to extend some conventional or like classical approach to implement graph distributed graph filter. And a quick review here is that like uh, in the we have this kind of like shift filter, shift operator or just a matrix. And of course, we start with a graph here. Something maybe I start with a graph here, and the shift GSP basically the graph cell processing is that on each node here, I can have a signal, so I have a scalar value as a signal. So therefore, like here, if I have 5 nodes here, then I can have a signal like x1 up to x5 here, and then we can define a shift matrix. It's an extension of shift operator in classic DSP. For example, like you can think of like an extension of like the Z transform, the Z operator in 1D DSP. And then if you think of like the shift operator, if we in 1D DSP, basically the Fourier transform, the sinusoidal basis in the Fourier transform is basically the eigenfunction of this C transform. And in GSP, graph cell processing, we just extend this idea and say we can have the Fourier transform basically is projecting our signal to the eigenbasis of this shift operator. So more precisely, if I decompose this shift matrix with like eigen decomposition to become like U lambda U transpose, then my Fourier transform applied to this signal, let's say this signal x, is basically U transpose multiplied by x. This will be a Fourier transform. Then I will have the frequency representation, like frequency. This is like kind of also extension of like classical cell processing idea. Will be basically the projection to each of different of the eigenbases, like, and we can based on different we can have a frequency filter, like at different frequency we give a different weight there. So maybe like I can at lower frequency I give like just like it goes, I have low pass and high frequency just as 0, and then I can do a inverse transform again. So then this would be a graph filter, basically this is a general graph filter, and in general I can just multiply them together, like just you can think of a single operator H, single matrix here H. And this H itself, of course, like the problem here is like we want it to be distributed implement that in a distributed manner. So namely that when I kind of like trying to compute the output of a signal values, I hope that I only take into the inputs from the current node and also like its neighbor. But okay, so what I want is like in the ideal case is like I want to have the support of my filter is same as the support of my shift operator. Where the shift operator, by the way, the shift operator typically will take, for example, the adjacency matrix. So therefore, it's just it will be just the matrix containing the maybe I will just give a precise definition. Aij will be just equal to 1 if like ij is the edges. So therefore, like we when we say that like we want, so basically like the if we force ourselves to have the filter has the same support as A or as S, then basically we cannot have like a filter. For example, like if I try to get the future output of like x5 here, I cannot get I mean, I cannot like use input like from other nodes beside like this node V here. And so, but of course, the local filter itself is extremely restrictive. So for that would be a classic approach. Is like we can consider not just S itself, but consider like high order of S. I mean, generally we consider a polynomial of S. So I have like, for example, a naught I plus a1s plus a2s squared, and so on and so forth, to get a filter to be represent to be like restrict to a polynomial of S. Then I know that like how to implement that in a distributed manner. But the problem is this is a very restrictive constraint here, and so therefore people try to extend that. Like first extension will be like, instead of like this is a scalar value, we can make this a diagonal matrix, d0 maybe d0 I plus d1 s plus d2 s squared, and so on and so forth. And we call this kind of approach a node variant approach, node variant filter. And in this paper, it's trying to extend further and to consider this edge variant. Basically, say we don't limit ourselves to just S here. Even in the most general form, we will have like h is just equal to phi 0 plus phi 0 times phi 1 plus phi 2 plus phi 1 plus phi 2 multiplied by phi 1 multiplied by phi 0, and so on and so forth. And each of these 5 here has to be a local filters. So therefore, like the support of like phi k here is the same as the support of s plus I. So I have this plus I because I also allow that for the diagonal. Basically, it doesn't matter the diagonal if because the diagonal element will of this filter matrix will be correspond to like I'm just taking signal from the current node. So I don't care like if I need to input use the input from the current node. So yes, okay, this is like the most general case, and then we have some a little bit more restricted cases. Like okay, it has like a constraint. This is known as a edge variant filter. So filter, I put 2t here, I guess. Filter, I can have a constraint. In this paper, they call it constraint edge variant filter. So for the constraint edge variant filter, say it will take the form similar to the earlier approaches. So we still use this s here. So we will have like h is equal to phi 0 plus like phi 1 s plus phi 2 s squared, and so on and so forth. And that's basically it. We have this constraint one, the general one. So now what we try to do is we try to look at these several cases, and we try to see how we can design the filter. So for example, like what we mean by design is like when we're given an arbitrary filter h here, so of course it still like it's not apparent that we can always find this phi 0 and phi 1 and phi 2 for this general edge variant filter, or like just find this phi 0, phi 1, phi 2, and so on, like in this form, such that like my h will be the same as this h. So we want to have this approximate h here, maybe written in this, given this phi 1, phi 2, and so on, phi 0, and hope that like my approximation will be close to this h. Maybe I use a different notation. Maybe I say like I have the HD is like the desired filter response, and I want to have this h is basically given by this here. So I want to find phi 0, phi 1, and so on and so forth, such that h is close to this HD here. Now, so let's start with the general case here that I have this edge variant filter. Oh wait, it's this one. Edge variant filter, the general form here. So, and we mentioned that like when we have a filter, it is shift invariant. So when we have a filter H is shift invariant, we have HS is equal to SH. The idea is that like similar, it's again like extension from the classical processing. Is that like when you have a filter, if it's supposed to be shift invariant, then you apply like this shift operator. Okay, let me give an example maybe. Oh, okay, maybe I'll skip it because I give this example before. I guess I won't repeat this example. I'll just give a pointer like to the place in my previous video. So let me just take it for granted for this video. I will put a pointer like you can look at the previous example there. I shouldn't keep repeating. So this is like the condition for shift invariant. So I have filter is a shift invariant basically. If this commute basically, if I have H commute with S, and here also like we kind of extend this kind of idea and saying that like we will have the filter, we have an H variant filter, we'll have this form here, right? We'll have a shift invariant H filter, a shift invariant H variant filter. If I have this 5051 and so forth, like they commute to one another or commute. So if they all commute like as I kind of like described in another video, actually I will give a pointer in my description as well. Is that like if you have two operator A and B commute, then and if all of them are diagonalizable, so in the sense if these guys are diagonalizable, then they can all be diagonalized using the same eigenvectors. So basically they share the same eigenvector matrix. So therefore like I may, if they are all commute for this shift invariant H variant case, so then I basically will have for all this 5k here can be represented as, let's see, as like U lambda k U transpose or U inverse. U transpose is equal to U inverse anyway. So so this eigenvector matrix again is the same among like all this fine here, just the diagonal is different. So therefore like if I substitute this into this one here, then what I have will be like my sum over, or maybe I just write it directly. So then my H then will be just equal to U sum over k equal to 1 to k and product j 1 to small k lambda j U transpose, something like that, right? Because I for example like I have like basically this is 50 is like U lambda 0 U transpose, and then like 5051 is a U lambda 0 U transpose and U lambda 1 U transpose. Then I have U transpose got cancelled, then I have lambda 0 multiplied by lambda 1, so therefore I have this product here. Then the next term again I will have U lambda 0 lambda 1 lambda 2 and U transpose and so on and so forth. Then I can pull like U and U transpose outside, so therefore I have U multiplied by this sum of product multiplied by U transpose. Now remember that like I want my 5k to be local, right? I want this to be local, and this to be local I can enforce that by introducing a new kind of matrix here here I guess in the paper use a rotation 5 script A here, and basically I will I just want to basically I will say a matrix is local if like phi script A multiplied by A is equal to 0. So what it does for this phi script A is just look at all these edges there, like one that's the corresponding edge. Okay, I'm sorry, this should be maybe I use this vectorized edge if and only if like H is local. So here I didn't specify what is this phi A yet, but what you can see, like I basically what it does is this is a building a matrix of let's see, the size should be number of I guess it's better to use an example to illustrate that. Number of columns will be just equal to m by n, I believe, and number of row is like how many places that like there's no edges. Maybe I just use this as an example. Then my phi script A will be something like I will have wow, that's pretty this is a pretty big, a little bit hard to show. I guess I better use a smaller example. So let's say I just have a simple graph like 1, 2, and 3. So I have 3 nodes here, and then I have connection 1 between 1 and 2 and connection 2 and 3. So what I want to make sure is that I shouldn't have connection 1 to 3 here. So what I'm going to do is my phi A will be basically just a matrix containing just one row, and I will have actually 2 rows, because I assume like one phi and phi 1 count as like 2 different edges here. So so let me put it more precisely. So I should have like 0, 0, let's see, 1, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0, 0, 1, 0, 0, something like this. So what happened is so as you can see, for this particular graph, if my filter is local, so for any filter for this graph, it should be phi by phi. So I should have no connection basically, like, because there's no connection from 1 to 3 here, my let's say this, I call it let me use H again. So I should have this H1 phi and H phi 1 equal to 0. These 2 places has to be 0. For all other places, maybe I can have different value, 1, 2, 4, 5, 6, 7, 8, let's say. Right? So because I have no connection from 1 to 3 here, so the support, like, let me show the support. Maybe let me show S plus I. So in this case, like, let's say for this graph here, if I define S as A here, is equal to I have 1, 2 connection here, and then I have 2, 3 have a connection here. So something like this, right? So therefore S plus I is equal to 1, 1, 1, 1, 1, 1, 1. So I need to have my support, and for any local filter should have support the same as S plus I. So therefore, like, these 2 places cannot be equal to, cannot be non-zero. So to enforce that, like, what I can do is I vectorize that matrix H here into one vector. So if like my original filter, original graph is like n, then my filter will be n by n here, and so therefore, like, this vectorized H should be n by 1, and then I will have just the row just to set the corresponding places that where there's no edges to 1, so that like if I enforce these guys to be 0, then I will just enforce like this these places that with no connection to be to have value equal to 0 in the filter. So that's the idea for the H phi A here. So that's how we going to enforce that H is local. So of course in this case we are not actually considering H again, we are considering for each of these phi k to be local. So therefore actually what we want is that we have this vectorized phi k multiplied by this phi A is equal to 0 for all k, right? K equal to 1 to big K here. And then yeah, this is one requirement here, and also like note that because my phi k can be written as this like U times lambda k times U transpose here, and we also show like in another video, I will put a pointer in the description there, that like U lambda k U transpose is equal to U transpose let's see, categorical product with U times I'm sorry, I should be vectorized of this guy is equal to U transpose this guy categorical product U and diagonal of the lambda k. So this is just taking the diagonal value of lambda k. So we have shown that before, so you may go back to that. Of course for this guy, like I can, it actually turns out it's just U here, or like U minus transpose as shown in the paper is okay as well. Here I assume stuff to be complex, to be real. So if you have like filters complex, then yeah, then it's important I have the inverse instead of just equal to U, I guess. So I have this one, right? So I have this guy, and again this is phi k here, is equal to this guy here, and also I have like phi a multiplied this is equal to 0. So I substitute this one into here now. So as I substitute, I have phi script a multiplied by U my inverse transpose categorical product U multiplied by diagonal of lambda k is equal to 0. And in the paper they like they call this like TU script A like this, call this matrix like this. So what you see is like, so what I mean is I can pick whatever for this lambda k. So I have this lambda k, and of course lambda k is a diagonal matrix here, and everything is 0 except the diagonal. And the diagonal I can pick whatever, but I need to make sure that this is actually in the null space of this TUA, right? So therefore if I call this, maybe I call this yeah, temporarily, let me just call it omega here. So I will have this omega is in the null space of TUA, and of course I may also like introduce another subspace. Basically, let's say if I have the span of some BUA, so in another subspace that the span of that is equal to the null space of that thing, then I will have omega is actually just equal to BUA multiplied by some vector here, right? So it's like linear combining the column vectors of this space here. Will and basically will always get me like the omega here will be inside the null space of TUA. It's a little bit just kind of like I would say a tautology in the sense even, but it once you find the null space here and you find the span here, now you have freedom. You just pick out arbitrary alpha here, right? It doesn't matter what you pick. Earlier, like it's kind of tricky to deal with like stuff to make sure it's in a null space, but if you change it in the span of that instead, then basically here now alpha is arbitrary. That become much easier. And with that, eventually we'll have this known as the proposition 1 in the paper. Let me write it here. Is basically we have 5k now. 5k is equal to what? 5k is equal to u lambda k u transpose, and my lambda k is actually a diagonal matrix with the diagonal equal to this BUA multiplied by alpha. So and that's it actually. That's it. We have maybe I just go to that directly. So we have so therefore we have the proposition 1 is saying that like for my 5k is actually have the form like u omega u inverse, where omega is equal to the diagonal matrix with the diagonal is equal to BUA multiplied by alpha, where BUA is basically the span of BUA is same as the null space of TUA, as I just mentioned earlier. And let's see. And then of course I can tell it because each of the 5k is equal to this one. Then my h here now, h here will be just equal to so my h there. So because my 5k is equal to u diagonal BUA times alpha. Let's say I put a k here, alpha k u transpose. So then like my h of course is equal to product of like this phi k is equal to 1 to big K here, and I have phi 0 ported to 5k something like, or actually maybe I write like this k to 0 something like this. So therefore it's actually equal to k equal to 1 to k. I can pull the u outside. So if I substitute this guy into this one here, I pull the u outside. Note that here is a product actually. So I just write a shorthand notation. So this, maybe I just write it explicitly again. So this is actually equal to j equal to 1 to small k phi j, something like this. So this is therefore is I have this product of diagonal j equal to 1 to k diagonal B U A alpha J U transpose or U inverse is the same thing. And that's our H basically. And we have the freedom. It's like pick this alpha here. So we can pick whatever alpha here that will give me different filters basically. And by the way, if we look at the filter here, of course, this is you can think of this filter here. If we have our earlier picture, that what we have with like Fourier transform, that kind of like interpretation, then I really have my filter is equal to, if I have signal is a U transpose, I am doing a Fourier transform, then I multiply by this part here, this sum and product here is the frequency kind of like the frequency profile, like what do you want to map for, what do you want to adjust, like this what do you want to weight for different frequency coefficients basically. And then you do the inverse transform again. This is Fourier transform, this inverse transform. So therefore, like what we are interested to look into for this part, the so of course like this guy here is a diagonal matrix because each of these are diagonal matrix, product of diagonal matrix is diagonal, some of them are still diagonal. And we want to look at the I element of this diagonal matrix that will correspond to the coefficient for the I frequency basically. So for this thing, let me just denote HI here. I'm not sure the paper. I think the paper is also called HI. So HI is equal to this like K equal to 1 to big K. Again, I'll just copy this again. Product J equal to 1 to small k, and diagonal BUA alpha J, and the II element. So what is this? So note that if I just look at this term, like diagonal of a matrix multiplied by a vector, and look at the II element. Maybe I have like, let's just consider a matrix A times B and create a diagonal matrix. Of course, this have become a vector, and this is the diagonal matrix, and I look at the II element of that. That would be equal to, if I just consider, okay, this would be equal to diagonal. Wait a sec. This would be equal to AB, the ith element, right? So, or this will be equal to sum over Aij Bj, and sum over J. And if I think of, let's see, oh, okay, yeah, I was a little bit confused. So then this is a basically say I just take a wall here, right? It's actually take the I wall here and multiply by the B here, right? So that summation is just actually taking the I wall, and let me call this I wall like AI transpose here, and multiply by B. So this is actually equal to like an inner product of AI transpose and B, or maybe I can just write in AI transpose B, something like and. yeah, again, like AI transpose, this is like the I rule of A here. So then we can use this to make this a little bit simpler. So I have a matrix multiplied by a vector, and look at the ith element just like this here. So therefore, like hi here is actually, I just put a bracket here. So therefore, it's equal to hi is equal to sum over k equal to 1 to big K. Now this m product also like j equal to 1 to k, and the I element of this guy is basically b u script a I transpose times alpha j. So here is basically the I rule of the matrix B U A there. So that is actually correspond to the second proposition of the paper. So here, so we have the hi there is equal to sum of product of this BUA I transpose times alpha j. So now let us look at the constraint version. Let's see. So I start with a new slide, a new page. Maybe I start with a new page here. We call that the constraint edge variant version will be basically something like phi 1 plus phi 2 s plus phi 3 s squared, so on and so forth. Remember that if I have an unconstrained one, I will just have phi 2 multiplied by phi 1. Here will be phi 3 multiplied by phi 2 multiplied by phi 1. So I have this is the constraint version. If I this is stand for constraint edge variant, and if I also like previously, if I also allow like shift-invariant constraint edge variant, that means that like my phi here, each of the phi commutes with my shift matrix here, the shift operator here. So therefore, like they share the same eigenvector matrix. So I will have like phi I can be written as a U diagonal, like oh, by the way, like again, like, because all the phi is like should be local. So from previously, my diagonal elements should be should have a form like that, right? So basically, this just make sure that I will have the phi matrix here basically will have 0 values when there's no edges there, when there's no edge there. And my S is let's say is also diagonalizable by U here with diagonal element is the lambda. In this case, lambda is a vector here. So here this guy is also a vector here. So something like that. I find like that as equal to like that. So therefore, like my H now will be basically U, or let me I just wait one more step here. So it will be basically like U diagonal B U A alpha 1, right? U transpose plus U diagonal B U A alpha 2 U transpose and times U diagonal, this is a lambda U transpose, right? So this basically could cancel, something like that, and then have many more terms. Then I can group the terms. I just pull out the U and U transpose outside. So I should just have like sum over K from 1 to, let's say, big K, and diagonal like B U A alpha K, and times diagonal lambda and this matrix to the power k, k minus 1 actually, minus k minus 1, and multiplied by U transpose, something like that. Now then, if I consider, again, like this is like the forward Fourier transform, this is like the inverse Fourier transform, and this corresponds to diagonal, of course this is a diagonal matrix, and the diagonal element correspond to the I frequency response, or the I frequency I frequency response to the in the frequency domain basically. So then I will, again, like the previous notation, I have hi here will be just equal to the ith element of this sum here, diagonal b u a alpha k, diagonal lambda k minus 1, the ith element of this guy. Again, like for this one here, previously we know we can simplify this into just the, let's see, the ith element of this diagonal will be just equal to BUAI transpose. This corresponds to the ith row of this matrix multiplied by alpha k, and multiplied by lambda to the k minus 1, something like, wait a sec, I should have a, yeah, I should have be the ith element. I'm looking at the I element, so this lambda I to the k minus 1, and that's it. So I will have the, therefore the ith frequency coefficient after the Fourier transform is scaled by this value here, and we have this is basically in the paper is referred to as the proposition 3, I think. Yeah, this proposition 3 here. He simplified further, like it's just a make it rename this like BUA I transpose I alpha k as this gamma ik here. So basically this guy here, you call it gamma ik. So now let's look at like how we design filter for that. So I will skip the parts that I trying to design the unconstrained one. So basically, like for the unconstrained one, for this guy will be phi 2 multiplied by phi 1 and phi 3 multiplied by phi 2 multiplied by phi 1 and so on and so forth. That one is as I mentioned in the paper, is a little bit hard to optimize. Instead, I have h kind of approximate as a I plus phi, or actually just phi 0 plus phi 1 phi 0 plus phi 2 phi 1 phi 0, and so on and so forth. Like I will have a constraint version, but basically it's like I have phi 1 plus like phi 2s, let's see, yeah, I can write like this, and phi 3s squared, and so on and so forth. And this is the constraint variant version. So I will look at two cases. First, I will first like starting like not assuming that like all these phi are shift invariant with respect to s. Basically, I'll assume that I phi here do not need to be like commute with s. So in that case, I just have basically this is my, I can adjust this phi here, and hopefully I want to have, let's say a h hat is a desired filter I want to design, and I would want to have find the phi here, let's say phi k as k minus 1, k equal to 1 to a big K, let's say, and I want to find phi here such that the Frobenius norm of this thing is kind of as small as possible. And of course I have some constraint for this phi here. I need to make sure that like, these phi are local, so therefore they should satisfy the support of phi k is equal to the support of s plus I. Now, so this look a bit difficult to continue how to we can optimize this. The standard trick here is like instead of like dealing with a Frobenius norm of a matrix, you just vectorize the matrix and consider just the L2 norm instead. So therefore, like this thing here, I can consider vectorize h hat minus vectorize this guy, vectorize this sum. Okay, sk minus 1 instead. So then I will get a vector, and then the Frobenius norm of this guy, basically Frobenius norm is just sum of square of all the elements, right? So after I vectorize that, it will be just simply equal to the L2 norm. So then, yeah, so I will consider this instead. And of course, I vectorize this sum here. This vectorization operator I can get into the sum instead, so I can have instead like sum over k equal to 1 k and vectorize this part. And here I will use the identity that we described in another video. I will give a pointer to that. So basically, if I have three matrices A, B, and C, if I factorize this product of these matrices, this will be equal to C transpose conical product with A multiplied with the factorization of B, something like this. And so what we can do is I can insert an identity matrix here, so before phi here, so then it become I multiplied by phi k multiplied by sk minus 1. So therefore this guy here will become like sk minus 1 conical product I multiply the vectorized version of phi k. Right? So I will have this instead. So, but note that like I have this phi k, I need to make sure phi k satisfy this constraint here. The support of phi k has to be equal to the support of s plus I. So what we can do is like here we will consider this sum, we will write it as instead of like having a sum here, I can write it as let's see, one. I can write it as like when k equal to I s conical product I and s square conical product I and so on and so forth, multiplied by a vectorized version of vectorized version phi 1 I guess, and then phi 2 up to let's say phi k. Right. So basically instead of the sum I will just write it as a row vector multiplied by this column vector. So it will be it's the same as the sum, because as I expand this multiplication out, I will just have I multiplied by this guy at s plus s conical product with I multiplied by vectorized version of like phi 2 and so on and so forth. Therefore like, I will get back this sum here. Yeah. So so maybe I include the summation here also, k by 1 up to k. So then of course I still haven't solved the problem with the constraint here, that I need to have the support of phi k is equal to the support of s plus I. So what we can do is I simply, when we compute the vectorized version of phi 1 here, So let me use the previous example, like very simple, like with 3 nodes, a graph with 3 node example. Then remember that in that example, like I will have the support is basically for this all these places I can have non-zero, but this one and this one has to be 0. So what we can do is we can simply, like, for this part is equal to 0, we can just remove that. So what we can do is when we consider factorial version of phi 1 here, I will basically let's say this one phi 1 originally have elements, like, let's say let me just call it simply oops, let me just call this phi 1 here originally simply x1, x2, x3, x4, x5, x6, x7, x8, x9, right? So as you see here, that means that like this one x3 here and x7 here has to be 0. So what we can do is simply exclude that, like we just remove that from the factorized version of this guy. So what we are going to do is that we will define something like phi 1 hat instead, and this will be like just the factorized version of this guy, but with the location, the corresponding location with no edges, we just remove that. So in this case, we have no edges here and no edges here, so therefore like we'll just have like ended up x1, x2, x4, x5, x6, and then x8 and x9. So, and of course, if we change this phi 1 hat here, so we need to change this kind of product here as well. What we are going to do, we can just remove the corresponding column of this matrix. So we'll define something we call this like S1 hat, and yes, let me just make sure. Yeah, actually I find phi 1 here, and I have maybe I put the S0 hat also here, S1 hat, S2 hat, and this is a S2 hat, and basically this S1 hat will be just equal to S conical product S with I. So again, if I use this example here, the size of S will be just 3 by 3. I have 3 nodes there. The shift matrix is also 3 by 3. I is also 3 by 3. Originally this matrix would be 9 by 9, right? But I will just remove the third column and the 7th column. So I will just remove like the third column and then the 7th column. Maybe I call, yeah, I guess it's clear. This is the third column and then the 7th column, because here I removed the third element of the 7th element of this vector here. So just I need to do the same thing. So I can basically do the same thing for all these. So each of the vectors here, I will remove all the places that the edge does not exist. Here, like respectively, I will remove the column that the edges does not exist. So then I will end up something like have this S0, S1 hat, S2 hat instead, and up to SK minus 1 hat, right? And multiply with this phi 1 hat, phi 2 hat, so up to phi k hat. So then what I will have like eventually is like this will be just like the vectorized version of this one, right? H, and I want this to be close to this guy here. in terms of the square norm. So to minimize that, then this becomes just a simple kind of like least square problem, because I can just take this as my random. This is basically my random variable. Like, let me call it x here, then my x here, and maybe I call this like a here. Then my x will be just the pseudo inverse of a multiplied by the factorial version of h. So that's how we may design a constraint h-variant filter that with like a particular, start with like h hat, and hopefully we will able to find this phi here such that like our implementation will be close to this h hat here. So this is for the case when we have non-shift invariant version. So if I assume that it's shift invariant, in that case, if I assume that this v1, v2, and v3, all of that kind of like commute with s, so therefore they share the same eigenvectors as s. So for the case with we also have the constraint that phi to be shift invariant. So namely, like phi's will be commute with s. So when phi commute with s, then phi will be share the same eigenvalue, or same eigenvector matrix, like u as s there. So I can diagonalize phi with like u here. So this is like from previous slide. So I can write phi as phi as a u multiplied by this diagonal matrix. That diagonal matrix with the diagonal is equal to the bua multiplied by alpha I. Alpha I can be anything. And remember, we have this because we want to make sure that like phi I is local. Then we can substitute this guy. If we remember, we substitute that, we have h. It ended up with this form. H will be just equal to u multiplied by the product of this sum of this diagonal of this thing multiplied by the diagonal of lambda to k minus 1. And again, like the diagonal, okay, this part is a diagonal matrix, and the diagonal portion of this matrix is the desired coefficient response, right? The desired frequency response. So let's say my desired frequency response, and I extract that as a vector equal to h hat. What I mean is, like, let's say I want this matrix to be designed as a diagonal h hat. So I have, or like you can think of like this portion here is a h hat. So then let's see, for this guy here, if given this lambda here, the frequency response as a column vector will be basically equal to k sum over k from 1 to k, and I can write this way. I can write diagonals k minus 1 and put to the front first, and then I look at the column vector. So I just, okay, remember this is a matrix, and this multiplied by column, and actually this should give me the frequency response as a column vector. So that means that I want this to be close to this h hat here. So and I can, again, like this, can write in a matrix form. So I can write it as a maybe like for each of this portion here, I call it mk. Then this become like a matrix form will be like m1, m2 up to m big K here. This is m small k here, m alpha 1 up to alpha k here, and then maybe this call it alpha here. So then this become very simple. Is I just want h hat again to have this second norm as small as possible. So then the desired alpha will be something like the If I call this A here will be the pseudo inverse of A multiplied by H hat.